Hello everyone, welcome back to my YouTube channel. In previous video I have shown you how you can use meshing for shared topology and non-shared topology. In today's video I will do a simulation for one of the geometry where I did meshing while using shared topology. And in this video I want to show you then when you are using shared topology you don't need to worry about the context at all. Those are being handled automatically. Before that let me show you the meshing. Here is our meshing. You can see the meshing in fluid, and in this base plate we have tetrahedral mesh, and if I zoom in further all those nodes are being shared between different zones. That's why we call this meshing is a conformal mesh that you get as a result of shared topology. You can also get this conformal mesh when you are using imprint in this space claim, but in this particular case we did use shared topology. Normally, when you transfer a geometry from your space claim or any CAD design, you get all those contexts automatically. You can see over here, we have these contexts. You can check all these contexts one by one, but you don't need to go into the detail of these contexts. As I said, because we are using shared topology, you don't need to worry about these contexts. Simply you can delete these contexts and you can see we will get the results as we have contact between these bodies. I have defined these 4 inlets over here, and these are 4 outlets on this side. Sorry, these were outlets, and here are these inlets on this side. Then this inflation name selection I had used for the meshing purpose, and this edge I have also used for the meshing purpose. And before going further, just briefly about this geometry. This geometry has 3 different type of zone. Let me call them. I have one is the fluid zone, which is indicating the fluid flow in these channels which are in the base plate. Then this base plate, it is of aluminium, and this base plate has this channel through which fluid is passing. Then on top of that I have these 12 cells. So actually in this simulation we want to study the cooling of these battery cell with the cooling plate or the base plate. Let's switch to Fluent. Our mesh has been transferred to Fluent, and I have converted tetrahedral into polyhedral. To convert your tetrahedral into polyhedral, you simply click over here and it will convert your tetrahedral mesh into polyhedral. I can show you the polymesh. For that, go to the graphics, in meshing, display your mesh, and select edge and faces. Select your entire mesh and say save display. Then you will get your mesh. Let me zoom in, close this one. In the fluid and the base plate, we had tetrahedral mesh which has been converted into the polymesh, and the battery cells were already having hexamesh, so it has not been converted into polymesh. So only tetrahedral is converted into polymesh. Now we will go all these steps over here one by one to set our simulation. Whenever I run simulation, I change unit as per my wish or as per my requirement. To change unit, you always come here in the domain. You go to the units, and for temperature, I mostly use degrees Celsius. Come in the quantities and click key. It will take you the temperature, and here you can select your respective unit. Then for mass flow rate, you come over here and press M. You will go to the all those quantities starting with the M, and I will say mass flow, and here I have already selected gram per second. You can close this one. Then in general you need to define if you are running steady state or transit simulation, or if you have any gravity. Then let's go to the model. In model I have activated this energy equation, and also I am using standard epsilon k epsilon model. You can choose whatever model you like. You can say OK. General models, then we can go to the materials. In material, I have to define 2 materials. One is for this fluid region, that is water glycol, and base plate is of aluminium, which is by default over there. Then I have to define for these battery cells. I have already defined those materials, but I can show you. can go to the materials. In fluid, if you come over here, it is water glycol. Let me open this one. You can see density 1000, Cp 3200, thermal conductivity is this one, and the viscosity is this one. You know how to define the material. And then in the solid, aluminium is always there by default. That I have defined new one, battery cells. I can show you how you can do that. For that, go to the new. You can say, let me call them cells. Remove this one, because if two material have same chemical formula, you will get an error. Then in properties, density I'm not changing, Cp I'm not changing, thermal conductivity I will change. In battery cell, you mostly have orthotropic thermal conductivity. It means the thermal conductivity from top to bottom or in all three directions is different. For this kind of prismatic cell, normally the thermal conductivity from top to bottom and from, you can say, from left to right or in y and x direction in this particular case is same, and in z direction it is normally much lower. We can define this thermal conductivity by orthotropic thermal conductivity. If you like, you can use constant, but I will be defining orthotropic. Here you can define the direction of your component. For example, here we have 1, it means first value will be corresponding to x-axis. Then in the direction 1, in the y we have 1, it means the second direction will be corresponding to y-axis. And the third one, of course, will be z. If I put over here 0 and I put over here 1, it means first value will be corresponding to the z-axis, second will be y-axis, and third should be corresponding to x-axis. Only one of the entity could have value of 1. I will leave as it is. So z direction is 1. Okay, it is already 1. In the y direction I have 24, and in the x direction I also have 24. I will say okay and change create. Want to overwrite? No. And then I have created new material of cells. Then we will assign these material to respective cell zone. For that, let's go to the cell zone condition. First we have fluid. In material we have only one fluid material, which will be assigned to all of the fluid zone. We can check that. Fluid 1 is the water glycol, and you can open all of these. All these will have water glycol. But in solid zone we have to assign, because we have 3 materials, so we have to check each material individually. Base plate is of aluminium. I can go inside, and base plate is of aluminium. If you want to change the material in the drop down, you can change the material, cell, battery cell, whatever you like. I can say close. Then in the cell we have to assign the material. Either you can assign battery cells or cell, and we also want to assign the heat source. Let's open battery cell or the cell 1. Here it is aluminium. We can change from drop down. You can assign cell or battery cell, both have same value, doesn't matter. I am saying battery cells. Then we have to activate source term. I will check this one, and source term will be activated. You will come over here and you will define source. Go to edit, and it is saying number of source. If you say 0, there will not be any source. If you say 1, there will be one source. If you would say 2, there will be two source. It's up to you how many source term you have. I want to define one source term, and that I want to define a constant value. Previously I did some video where I have shown you how you can use expression or the input parameter. You can check those videos to see how to use as expression or as an input parameter. And I am using this constant value. Let me just remove all those decimals. 2700. Okay, apply and close. We can copy the cell zone condition to all those battery cells very easily. Right click, say copy, and here you will select the cell zone from which you want to copy the condition. I want to copy from the cell 1, and here you will select all those cell zone where you want to copy your condition. I want to copy to all these except base plate. And one more thing, here I have selected only solid, and here you will see only solid zone will be present. If I will select fluid over here, you will see only fluid zone over here. So that's pretty smart. Okay, let me select solid cell 1, and then I will select all these and I will deselect this one. I can say copy. Yes, I want to copy from cell 1 to all those selected cell zone, and close. Now we can verify one of the cell zone. Open this one. Material is same as we did before. The source term has been defined. We have one source term. Go to edit, and you can see one source term which has a value of 2700. This practice saves a lot of time. Now we can move to the boundary condition, to the inlet. Here I have velocity inlet. First I want to change to mass flow inlet. Select all these, right click and say type to the mass flow inlet. The type has been changed. Now I can open one of the velocity inlet. I can set the mass flow rate, which is 0.75, normal to the boundary. I'm not changing turbulence boundary condition, but I will change temperature to 20 degree. Apply and close. You can do same with all of these. You can open one by one and change all these, or you can do same as we did in the cell zone condition. Can say copy, and I want to copy from inlet to rest of the inlets. I will select all these, say copy, OK, and I can close. Then in internal, you don't need to do anything. In outlet, you don't need to do anything. If you wish, you can change outlet whatever you like. If you have some other condition, or if you have some boundary condition, outlet temperature, but this one is only for the backflow, but the actual outlet temperature will be calculated. And also, if you want to change the type of outlet, by right click you can change the type of the outlet. Then we have wall. All those walls have been transferred over here. For example, let me open this one. This one is the wall of the cell 1. If I have any convection or anything, I can define on this cell wall. For example, I can come over here, I can define convection. I will do a detailed video how you can define this one. But for the time being, we are not doing anything. And here you can see we don't have any interface tab. Normally when you use non-shared topology, you would have another tab over here with all your interfaces. Okay, then in the report definition, I have defined one report for the outlet temperature. For the report definition, you can check my previous video. But here I have defined mass weighted average outlet temperature. We have defined all those conditions over here. One more thing, residual, if you like, you can change residual. For energy, 6 is okay, it is at the boundary, but if you want to have better conversions, you should use higher. For energy, it is recommended to use at least -8, -9. And then in initialization, I will be using standard initialization, and calculation I will run for 500 calculation. I can right click and say initialize and calculate. Yes, it is asking if I want to use this setting for the current calculation. Okay. And now my simulation has been started. Meanwhile, I want to show you a verification step for our simulation. For that, I have a small Excel sheet. Here I have added all these parameters. In this simulation, we have 12 battery cells. Heat per cell is the 3 watt. This one is the cell volume that you can get through space claim in meshing, or you can also get in Fluent. It's up to you how you get that. Heat density, this value you have seen I had provided in the cell zone condition, which was watt per meter cube. In Fluent, heat is always provided into the watt per meter cube, or you can say heat density. So you get heat density by dividing these two values, this and this. This one is the total heat generation in this system, which is 3612 into 3. Actually, in this Excel sheet, I want to show you the expected outlet temperature that we can do easily by the heat balance. So we know 36 watt we are providing to the battery cells, and we are running the steady state simulation. in steady state simulation, you always get heat balance. It means whatever heat you will provide, it should be balanced by the heat taken by your fluid. So we are providing 36 watt, and based on this heat input, we want to calculate the outlet temperature. 3 gram per second is the total mass flow rate. In the fluent, I have given 0.75 gram per second, but we have 4 inlet. It means in 4 inlet, we have 3 gram per second. Fluid CP or heat capacity is the 3200 joule per kg per Kelvin. This one is the expected delta T that you can calculate by this formula, simple heat balance formula, MCP, we can say delta T. In this formula, we have Q, which is the heat input 36, we know M, which is 3, we know Cp, which is 3200, and we can calculate our delta T. I have put all these values in this formula and I got 3.75 degrees Celsius, which is the temperature gradient from inlet to outlet. Or we can check at the end of simulation if we get this temperature, and it will verify our simulation results. Our simulation has been finished and it has been nicely converged. One thing I want to show you, we have some reverse flow, 0.3% area on the pressure outlet of 67. If we go over here, it means this one is our pressure outlet where we have some reverse flow. There are different ways of avoiding this reverse flow. In this particular case, you don't need to do anything special. You just run this simulation little longer by reducing your residual, and this reverse flow will finish. But I want to show you results. Let's open our results. I want to create a new result. Let me call it temperature. I want to plot temperature, all those temperature, select all those bodies, save display. That's how our temperature distribution look like, and I can already see it is feasible, or you can say plausible. Few things I want to tell you. Here is our inlet, and our inlet temperature is 20 degrees Celsius that you can see over here, and on the back side is outlet, and the outlet temperature is somewhere here. We can exactly check what is our outlet temperature, but the fluid temperature is increasing from inlet to outlet. Similarly, battery temperature is increasing from front to back or from inlet to outlet, because we have fluid at higher temperature over here, so that's why the battery temperature should be higher on the back side or near the outlet. Also, from top to bottom of the battery cell, temperature is decreasing, which shows the cooling of the battery cell. I can create some plane to show you what is happening in between, but before that, let me calculate the exact outlet temperature, because as I said, we were expecting a delta T of 3.75. For that, go to the report, go to the surface integral, and select from here mass weighted average. Go down, mass weighted average, select temperature, total temperature, and we want to check the outlet. So select all of these outlet. Compute 23.71. Our inlet temperature was 20 and outlet is 23.71, a delta T of 3.71. We were expecting a delta T of 3.75. It means we have a difference of 0.04 degree Celsius. If you remember at the start, or when we were setting our simulation setup, I told you that residual should be -8 for temperature. If I would have used over here -8 or -9, we would get closer, but of course there will always be some numerical error. Another one, I can create a plane through fluid and one plane at the battery cell. For that, let me go to the here new surface, then you can go to the plane, and here you can already see a plane. There are different methods of selecting a plane. I want to create a plane in XZ. Here you can see the plane should be in the XZ. I can select XZ, and then you can set the Y value. By default it is at the center. You can change value over here, or you can move through this arrow. I want to move little down, and I can zoom in and check. Okay, little higher. Now it is passing at the center of the fluid. I can say create, and I can give it a name, fluid plane. Fluid plane. Create. Then I want to create another plane. Let me call it cell plane or cells plane. For that I can move this one little higher. Let me zoom out. Zoom out. I can move it over here, and I can say create. Then I can close here. Those plane will be here. I can go into my surfaces, minimize surface plane. I have a lot of planes, but freshly created cell plane and fluid plane. I have some previous plane. Let me select this one as well, and I can say save display. Here you can see this one is our fluid plane, and these two through cells, and the temperature of the fluid is changing from inlet to the outlet. And also you can see there is a temperature gradient between these two planes as the temperature is changing from top to bottom. So these results make sense, and these are quite plausible, and the temperature of the cells as well as of the fluid is changing as expected. That's it for today. I hope you found this tutorial helpful. Thanks for watching, and see you in the next video.